Hello and welcome to our next video here, 1.3, where we're going to talk about how to measure sort of the center of a distribution, among some other stuff. Really, this video and the next video, we're going to go over the ideas of how to describe the distribution you're looking at. And when you do that, you're supposed to describe sort of 5 different things there: context, shape, center, spread, and outliers. So today we're just going to go over the first of those 3: context, shape, and center. And it has a little acronym with it, as you can see there: CS, CSO. Some other, different teachers have different acronyms, but we like to go with CS, CSO, because it's kind of got like a good rhythm to it. Kind of sounds like E-I-E-I-O from the McDonald's song there. So yeah, the CS, CSO, we're going to go over CSC today. And the next video we'll go over SO, and then we'll loop it all together there. So let's talk about the very first one, the first C, context. So it's important that you describe what's being compared, analyzed, represented in any sort of display. So you're going to look at like, what are the labels, what units do you see, and sort of mention that. So I like to do that right away. I like to sort of kick it off right away, like the distribution of, and then fill in the blank with whatever the context is for the distribution. So it's not really a crazy thing to think about, but you do want to make sure that you get the context in there. The next thing is shape. So this is where we sort of look at what does the distribution sort of quote unquote look like. And a couple ways to do that. The first is to describe how many modes that you see. Mode is kind of being used similar to maybe the definition you remember from back in like middle school. Mode is just like the most frequently occurring value in everything. What that means visually here is like how many like humps or hills does it have? So sometimes it might have just one. We would call that unimodal. So this is an example of a unimodal distribution there for the, looks like the price of homes, if you read the labels there. So just one big hump. Or it could be described as bimodal. In this particular example here, diastolic blood pressure, looks like there's 2 peaks there. So, if these are people that we're, taking the blood pressure of, there's like, a lot that show up in this little range and a lot that show up in a different little range there. So bimodal. And I guess you could continue thinking trimodal. If it gets more than that, you might just say multimodal, but you don't really see those naturally occurring in too many places. Now, if there's like not like if your gut was like, well, like everything's a mode, or there is no mode, everything's kind of just like like about the same height of those bars, we call this approximately uniform. And I put the little tilde there to be approximately. You could write out the word approximately or nearly or roughly, some sort of word that signifies like it is not perfectly uniform. If all of those bars were literally all the same height there, then I guess we could say, yes, that is exactly uniform. But again, that won't naturally occur too often. The next way we can describe it is sort of talking to its symmetry. So is it symmetric or not? And if it's not, sort of how do we know? So the way that we sort of talk about symmetry is, well, we'll start with the middle one. That one there that you see in the very middle, that we would call symmetric. And since it's sort of an ideal curve, it is actually exactly symmetric. But again, naturally, out in the world, when we collect data, things might be roughly symmetric, approximately symmetric. So we definitely want to try to use that word approximately or roughly when describing those things, because it's probably not true that it would be exactly symmetric. Otherwise, we call them skewed. So each of these on the left and right are representing skewed distributions. And the skewedness of these things have direction to them. And it's a little confusing at first, but it's important to keep this straight in our head here. So this thing here this one here is a skewed left distribution. Okay, skewed left. And how do I know that? Well, it has to do with the tail, Where's the tail? The tail is over here on the left. That's the skewedness there. That's where it's skewed, is that tail is skewing it to the left. So that would mean over on the far right here, that is skewed right, because again, that tail. So when you're looking for what type of skewed are you seeing in your distribution, you're looking for the tail, not where the hump is. The hump doesn't tell you which way it's skewed, it's the tail. Okay, so that's a really important thing to remember. Look at the tail. All right, and so let's continue on here. Oh, and I'll take notes that, you can see there some of these measures of center are being sort of represented in there. We can come back and look at those in just a little bit. So let's talk center. Center is our next thing. Center, we have two ways of measuring center. Okay, so center is an attempt here to sort of say what's the typical value for a distribution? So you're trying to sort of boil down a big distribution to a single number if possible. So there are two ways to do that in this course. The first one is the mean, okay? That's what usually people talk about when they say average, is that they're talking about this. It's the arithmetic average. This is where you add up all the data points and divide by the number of data values that you have. And so that's denoted in two different ways. If we're dealing with a sample mean, okay, so if we're talking about I just grabbed, 10 people from a class or, 100 people from a school, then we represent that with something called X bar. X bar. So if you see X bar, that's telling you, hey, that's a mean. So that is a calculated average like it's being described, and it's for a sample, okay? The other way to denote it would be to be thinking about the whole population. If you're talking about all, babies, all American baby birth weight, and you're thinking about the whole population, every single baby that's ever been born, the mean of that is this Greek letter here that looks kind of like a U with a tail on the front there. It's actually not a U, it's sort of like the Greek letter for an M, and it's mu. Not meow, not moo, mu. So if you see that, that's letting you know there's obviously, this is a population. This is trying to talk about the whole thing. It says for later because oftentimes we don't actually know every single data value in a full population. A lot of what we do in statistics actually is trying to kind of think about that and figure that out. But that's something we'll get to later on. Now I want to take a quick moment to sort of talk about the formula sheet for this class, okay? We should have handed this out to you already. If not, we're sorry. And I wanted to sort of take our first chance to look at oh, hey, we have a formula here. Yeah. You might notice that right here, there's X bar, and it's sort of showing the calculations we're talking about there. So this is for a sample mean. You can label it on your formula sheet if you'd like to. So that is the sample mean formula right there. That's little E thing that you see there. That is actually not an E. That's a Greek capital S standing for sigma. And it's saying the sum of all the things. So it's saying take the sum, add up all of your data values, and divide by n. So both ways that you see here are equivalent to each other. So it doesn't matter if you multiply by 1 over n or divide by n. Those are the same thing. Now you might be wondering, well, wait a minute, there's not a population mean formula. It turns out it's actually the same thing. You would find it the same way, add up all the data values in the population, divide by the number of people in the population. But you might, if your eyes were wandering, notice oh, wait a minute, I'm noticing some mu's down here. What is that all about? Yeah, so later on we're going to get into sort of different distributions for probability. And we'll be talking about using mu then as well. And I believe the next page has mu pop up as well, as you can see, with lots of what we call subscripts. So these things that are like p's and stuff like that, those are subscripts that sort of help us differentiate, is this the mean for this type of thing or this other type of thing, you get a chance to sort of like label things. If you've done physics before, you might be fully aware of this. But yeah, and we can see as we keep going down, the mu's keep popping up. There's a lot of other stuff going on. We are not concerned with any of that right now. I just want to show you that mu is popping up in some of our other stuff we'll be dealing with. Right now, all we're focused in on is this sample mean. So if you ever forget what the formula is for sample mean, then it's right there for you. So the other measure of center is median. Median is literally just the middle value of your distribution. You just sort of take all of your data and you just chunk it up in half. Like the best way to do it if you're doing it by hand is you list everything from least to greatest, and then you just figure out where's the middle value, okay? Now, if there are an even number of data values, okay, so like if you had 50 data values, then there actually is not a middle value. So instead, what you do to make sure that you get this correctly here is that you're going to take the mean of the two middle values. So in that case, you're going to go ahead and just be like, oh, data point number 25 and 26 of my total 50, take those two data values, add them together, divide by 2, and that gets it. So sometimes your median ends up being a data value that actually is not in your list just because it's halfway in between a couple of them. Now, there is a notation for median that I literally have never seen before until I started teaching this, so don't have to like store this in for memory. Apparently, if you do an like X tilde or an X, I don't even know how to say it out loud, to be honest. That's how little we use it. That represents a median. But I'm never going to use that on a particular homework test or whatever, so don't worry about that too much. Cool, so that's center, mean and median. There's two ways to do it. And so a natural question that pops up a lot is sort of like, well, how do you know which measure to use? Like, is there, like, should you always talk about both, or are you supposed to talk about just one of them? And if you're only supposed to talk about one, like, is it always mean? Is it always median? Well, there are certain scenarios where one is better versus the other. And so I'd like you to sort of pause and take a look at the 4 dot plots that I've shown here. And I'd like you to think about, like, what number is sort of a typical sort of value for these 4 different distributions. We've got pets, we've got number of siblings, we've got measurements of a hallway, and we've got quiz scores. So as you look at each one of those, you would say, typically the number of pets are this. And I'd just like you to sort of think about that for a little bit. So go ahead. Okay, so hopefully you paused and you sort of thought about that. What I'd also now like you to think about is, do you think the median, the 50% mark for the data, is doing a better job at matching what you said was the typical value? Or do you think the mean is doing a better job? Or maybe it's that both are doing it. So take a pause again and sort of look back at each of these and think about, well, where about is the mean or median, and which one's matching better what I said was a typical value? All right, so this helps us come up with sort of what is the best way to describe these things. So mean actually is the one we try to default to as much as possible. Since it's a calculation, that's really important for us, that it's calculated and not just like plucked out from a number like the median is. So in this case, we try to use the mean whenever we can. And we only really use the mean in one scenario that we're looking for. So the distribution, if it is approximately symmetric or uniform, because uniform usually implies symmetric as well, with no outliers. So if your distribution is roughly symmetric and or uniform and there's no outliers, then you're going to want to use the mean. That's the one you want to lean on. So here, this one up here in the top right, talking about the hallway length, mean would be a really good option. That's roughly symmetric. There aren't any outliers. And so that would be a good way to sort of try to measure that. Now, when do you use median? Pretty much in all like the other cases. So the scenarios, if the distribution is skewed left or skewed right, That would be a scenario when you would want to use it. Another way would be that if it has outliers, you would want to use the median here. Let's think about why those would be the case there. So if you look at sort of things that are skewed up here, number of pets is heavily skewed. Why would I want to use the median? Well, the median, you probably looked at this and said one pet is about the typical number of pets, right? Well, the median isn't too far from that. Or maybe it is like 1 or 1.5 or something like that. But the median is like going to be here or here, 1 or 2. But the mean is going to be much larger than that because there's these, like big long tail from all of this. You can see that we got several people that have 5, 6, 7, 12 pets. When you put that into the calculation for a mean, that's going to pull that mean much further to the right. So the mean ends up over here somewhere, which is not doing a great job at sort of saying, like, you wouldn't look at that and go like, yeah, 4 or 5 pets, that's pretty typical. Like, that's not the case. 1 or 2 pets, 0, 1 or 2 pets, that's the more typical type of number of pets. So you don't want to use it in skewed scenarios, the mean, because the mean will not be representing a typical value better than the median does. So use median here. And for the same reason, we want to use median here as well when it comes to the number of siblings. So you probably looked at this and said 1 or 2 siblings. That is the typical value there. But there are some people that have 6 and 10 siblings. So when you go to calculate the mean ends up getting pulled over to the right. And so because of that, even though you have a roughly symmetric thing here, these outliers are going to pull that median. Sorry, the mean, going to pull that mean over towards them. And so you're going to end up with like, oh, well, my mean is like 3 or 4. And that's not really a good representation of what is a typical number of siblings for this sample. Another scenario that is not on our list here when you would want to use the median is when your display is a histogram. So if your display is a histogram, you can't really tell where the exact mean would lie because you just have buckets. You just have these bins that you're looking at. And so it's not really easy to go like, and the mean is this. So if you have a histogram, it's best to just go with the median, and that would be just totally fine. And then you would just give it as sort of a range of values. The median is somewhere between blank and blank because you only have your bins. Now, you might be wondering, well, wait a minute, hold on. We had another display up here that we didn't talk about, quiz scores. Which one does better there? Turns out neither of the mean or median do a good job here. It's roughly symmetric, so you'd find that the mean and median are probably about the same, around maybe like a score of 5, but nobody would say that 5 was a typical score here. So anything that's bimodal, you tend to not want to use mean or median, and instead you would say like, it's bimodal, and has modes at 3 and 7. So that pops up every once in a while. So just keep that in mind, is that if something's bimodal, don't go leaning into this idea of like, what is center? Because this is a scenario where center isn't really a good measure for anything. All right, so to finish up, you're going to practice your new vocabulary here and come up with some descriptions. So for each of these, you're going to describe the context, shape, and center of each distribution using what we just learned above, with a very huge focus on like which measure of center are you leaning towards and why. Okay, so I'll just look at these things really quickly. So what was given here first is a sample of 100 California household incomes in thousands of dollars. Okay. And then we have here a STEM plot that is helping us see how many questions were answered correctly out of 50 on a quiz test. You can just sort of decide there. So you can see the key there that 1 and then vertical line 2 represents 12 questions correct out of 50. So go ahead and fill those out. And when we come into class, you're going to be sharing this with your neighbors and making corrections and asking questions.